one. Because otherwise it's quite hard unless you're a pedant and always sort of double checking yourself. It can be easy to get confused. Right, so now we know what this flow is, what it's useful for. Let's take a little bit of a more microscopic look at it. What's actually going on within the metals? Those of you who do chemistry, you might recognize this as a giant metallic structure. You've got ions, and you've got a sea of delocalized electrons that aren't associated with any particular ion, and they're free to move between the ions. Great, love it. In a piece of metal, the wire, before we connect the battery, these electrons randomly move. Yeah, and they drift around at high speeds, but not really going anywhere. They're just doing, rapid loops of the neighborhood, going around the block several times at high speed, but the net movement of them isn't going neither here nor there. Until we connect a battery. What the battery does, it applies a field all the way around the wire in a direction. So we'll apply a field going right to left. That will drive the current around in that same direction. Bear in mind that the field is defined as the direction in which positive charges move, and the current is defined in the direction that positive charges move. But in reality, it's the negative charges that are actually doing the moving. Okay, so my battery, I connect it, it provides a nice field for my electrons to, electric field for my electrons to I was about to say follow, but technically, again, they're moving in the precise opposite path that my field is generated in. Okay, so there's a net flow of electrons towards the positive terminal, and they do so at this speed called the mean drift velocity. So the actual velocity that each electron is moving is very, very fast. They're very small particles. Their mass is very, very small. It's 9.11 times 10 to the minus 31. So, they're almost nothing, the mass. So they individually move very, very fast. But as a flow, this sea of delocalized electrons, how fast does that move along our metal? It's not actually tremendously fast. It's sort of normally millimeters per second or maybe centimeters per second, several millimeters per second. Electricity, in terms of the actual useful energy, doesn't actually flow through the wires very fast. But because all the electrons at all points in the circuit are moving together, that's why when you push a switch, the light immediately comes on. It's not that the electron that was waiting by the switch suddenly rushes up to the projector or whatever it is. It's that electron pushes on the next one, and they all push, and the energy that wave that propagates to the electrons reaches that fast. None of this you entirely need to bear in mind, but for those of you not sitting exams this year, perhaps if you're doing the full A-level course and you're in year 12, it's good to know what the fundamentals, what's actually going on here, because it makes the year 13 course make a little bit more sense, I think, when you talk about capacitors and inductors and so on and so forth. Okie dokie, right. Enough of that. The mean drift of charge carriers creates a current which can be calculated with the transport equation. So I've now applied my battery. This is a sort of zoomed in section of wire. And this wire, oh, sorry, it's a bit rough, but there you go. This wire has a cross-sectional area of A. The current flows is the number of electrons multiplied by the area, the cross-sectional area of this wire, multiplied by my mean drift velocity times the charge of each electron. Okay, so let me define these on the right. No, number of electrons. E is just the charge of each, so N times E is the total charge of all the electrons. The area is cross-sectional area. V, that's the mean drift velocity. Let's check, is that all watertight? This current, this is current. For historical reasons again, we use the symbol I, which is slightly annoying because you'd want to use the letter C, but whatever. We're just gonna have to get over it, aren't we? Current is in coulombs per second. That's a very wonky C, but forgive me. This charge is in coulombs. This is in meters per second. This is in meters squared. I knew there was something slightly wonky. It is the fact that N is not the total number of electrons, it is the number of electrons per unit volume. Okay, so take a sample of this metal. How many delocalized electrons are in it? That density of electrons is my letter N. Okay, and I think it's probably worth erasing my scribblings. And there you have it, the transport equation. Doesn't necessarily come up often, but from time to time. It's also on your formula sheet. So you don't necessarily need to commit it to memory, but you do need to be familiar with what each symbol means. They won't tell you that on your formula sheet. Mean drift velocity. N, remember, it's the number of electrons per unit volume. Okay, let's do an exam question. In 1909, Robert Millikan devised an experiment to measure the negative charge gained by oil droplets. This is the experiment I was referring to earlier, which had gained electrons. He found that all the oil droplets had charges that were integer multiples of an elementary charge E. Explain this result. 3 marks, so we expect to make 3 points. So you'd say, you know, the charge of the droplet is all the total number of electrons in it multiplied by the charge. All electrons have that elementary charge, and therefore it's impossible to get a non-integer value. Let's see how that matches up with the mark scheme, perhaps. What would the charge of the droplet depend on? Okay. Yes. Okay. Charge of the droplet is equal to the total charge of the gained electrons. Yes. All electrons carry the negative elementary charge E. These are just physical basic facts. Remember, start with our explanation questions. We just want to state what is true. All electrons carry E. The charge of the droplet, you know, what is that? And then 1 point, sort of logical deduction. So the pattern of a good 3 mark explanation is fact, logical deduction. Or induction. I always forget the difference between those two. I'm not a logistician, or whatever they're called. Deduction. Okay. Therefore, the charge of the droplet is dependent on the number of gained electrons N, rather than some continuous variable.